Video 2H, Error Propagation. You've watched the earlier videos, and you now have taken a set of measurements and calculated the means and the confidence intervals, or you've looked up the noise or uncertainty for a part from a data sheet. You now need to use the measurements or data sheet info into a formula and estimate the confidence intervals of the results. This video will discuss both analytical and numerical methods for calculating the confidence intervals. Let's motivate the issue with an example. Suppose we have a voltage divider as shown in the figure. R7 and R8 are standard 1% parts, and V3 is a 3.3 volt voltage regulator where the spec sheet shows it is good to 3.3 volts plus or minus 0.05 volts. You should all be able to calculate the nominal output voltage V out. But how do you calculate the uncertainty? Do you just add together the uncertainties in each component? How do you add percentages and volts? Do you convert the percentages to ohms? How do you add ohms and volts? If you haven't seen error propagation before, or if you don't remember how it works, think about how you might do it. The first question you have to ask is, are the errors or the uncertainties in the components correlated or independent? Unless you have a good reason to suspect otherwise, assume they are uncorrelated independent random variables. In that case, we know from statistics and or advanced systems and signals that we add the signals in quadrature or in a root sum of squares sense. All well and good, but we still don't know how to add ohms and volts. So what do we do? There are two principal methods to go about calculating the error. The first is numerically. We start by leaving the other variables at their nominal values, the same as setting their uncertainties to 0, and seeing how much the result changes for the uncertainty in the remaining variables. Let's go through the process for each of the variables. First, the equation and nominal value for the voltage divider. V out equals V3 times R8 over the sum of R7 and R8. In our case, the nominal value calculates to 2.2 volts. Next, set R7 to its maximum value. 10 k ohms plus 1% equals 10.1 k ohms, which is plugged into the equation, giving 2.193 volts. 10 k ohms minus 1% equals 9.9 k ohms, which is plugged into the equation, giving 2.207 volts. Likewise, for R8, we get 20.2 k ohms and 2.207 volts, and 19.8 k ohms and 2.193 volts. For V3, we get 3.35 volts and 2.233 volts, and 3.25 volts and 2.167 volts. Calculating the errors for the maximum in the confidence interval, we get negative 0.007 volts, 0.007 volts, and 0.033 volts for R7, R8, and V3 respectively. For the minimums, we get the negatives of the previous values, 0.007, negative 0.007, and negative 0.033 for R7, R8, and V3 respectively. Let's add either side in the root sum of squares sense. The result is plus or minus 0.035 volts. We can then state that V out equals 2.2 plus or minus 0.035 volts, which is our desired answer. For the technique to work, all three uncertainties need to be at the same confidence level, for example 95% confidence. If we don't know the confidence level in a data sheet, we can still use the value. We just have to recognize that there is possibly an error in our error. If all three have the same confidence level, the resulting uncertainty is at the same confidence level, for example 95%. Note that by comparing the uncertainties contributed by each component to the final result, we can see that the voltage regulator contributes almost 5 times as much error as the resistors, so our most effective means for improving accuracy is to get a more accurate voltage regulator. The numerical method of plugging in each confidence interval certainly works, and we can make the procedure somewhat easier with a spreadsheet, but it is tedious and doesn't give us much insight into what's going on. That brings up the second method. Assuming that the noise or uncertainty isn't huge, what we're looking for is how a small change or perturbation in an input to a function causes a perturbation in the output of the function. In other words, how the output of the function changes locally with the input. To me, that sounds remarkably like the partial derivative of the output with respect to the input, and indeed it is. Let's formalize this a little, probably not enough for the mathematicians, but enough for us. Assume we have a multivariate function f equals f of x, y, z, dot, dot, dot. In our example, v out equals v out of r7, r8, and v3, or more specifically, v out equals v3 times r8 over the sum of r7 and r8. Assume that the residuals are reasonably small and have good approximations for the errors. Then let's do a Taylor series expansion about the true value for all the variables and only keep the first terms. The result is given here. If we substitute in epsilon sub I for each of the differences, we end up with the following. In other words, the error in f is the change in f with x times the error in x plus the change in f with y times the error in y plus the change of f with z times the error in z, and so forth. If you have a set of known small perturbations, the formula will permit you to calculate the perturbations in the function exactly. However, we're trying to see how randomness or uncertainty in the input affects the randomness or uncertainty in the output. So we'll assume that the errors are uncorrelated and add the contributions in the root sum of squares sense. Taking the partial derivatives, in our case, dv out dr7 equals negative v3 r8 divided by the quantity r7 plus r8 squared, or substituting back in for v out, negative v out divided by r7 plus r8. dv out dr8 equals v3 r7 divided by the quantities r7 plus r8 squared, or substituting back in for v out, r7 over r8 times v out divided by r7 plus r8. And dv out dv3 equals r8 over r7 plus r8, or substituting back in for v out over v3. Substituting back in for v out often makes the formula simpler to calculate. When we use the formula with the substitution, we use the nominal calculated value for v out. Substituting the partial derivatives back into the expression for the error in v out, we get the following expressions. The first is without substituting back in for v out, and the second is substituting back in for v out and factoring out v out. Since we're assuming the errors in r7, r8, and v3 are uncorrelated, we need to add the errors in the root sum of squares sense. We've factored out v out, which we know to be positive in this case. We'll now plug in the nominal values for r7, r8, and v3. When we plug in the errors or uncertainties, we need to convert them from percentages to actual values as necessary. Failing to do so will really mess up your error calculations. Simplifying and solving, we get 0.0349 volts as the confidence bound. So we report V out as 2.200 plus or minus 0.035 volts. If we knew the confidence level, we'd report it here as well. You'll note that this version agrees with the value from the numerical method. The two will agree as long as the uncertainties are small enough that just the first terms of the Taylor series are sufficiently accurate, which is almost always true for reasonable uncertainties. Again, comparing the three terms, we see that the contribution from the voltage regulator is the largest. Let's do another example using a negative temperature coefficient, the thermistor. The relationship between absolute temperature and resistance of a thermistor is modeled in one of two ways, either with beta and the reference resistance at the reference temperature, or with the Steinhart-Hart equation. The beta form is accurate enough for temperature excursions of plus or minus 10 K about the reference temperature, so it is the form we will use here. The reference temperature is almost always 25 degrees C or 298.15 Kelvin. A batch of thermistors will be manufactured with the intent of having specific beta and also a specific resistance, frequently 10 kiloohms, in our case 1 megaohm, at the reference temperature, but manufacturing variability gives rise to uncertainty in beta and R naught. The manufacturer will usually specify the uncertainty in the datasheet. For this example, we will assume that the error in R naught is small compared to the error in beta and the error in the measured temperature, R. We'll do the analytical method first. Taking the partial derivatives of t with respect to beta and R and then subbing in, we get this expression. Subbing back in for t, we get the following much simpler expression. In case it isn't obvious, we'll replace the differentials with the error bounds or uncertainties for beta, R, and t. We'll make the substitutions into the root sum of squares form and plug the values into the simple spreadsheet. In this case, the nominal value of beta is 4261 with an uncertainty of 1% and the measured value of resistance is 3.7 megaohms with an uncertainty of 10%. The error term from beta is 0.23 K, and the error term from R is 1.75 K. The least sum of squares result, giving the error bound in T, is 1.77 K. The result is reported as 2.74.14 K plus or minus 1.77 K. This is the numerical method version of the thermistor error limits. The nominal values were entered into the second column, and the formula for T was entered into the cell below. The values and formulas were dragged right or copied and pasted into the next four columns. The relevant cells were changed in each column for the correct uncertainties. The delta T's for the plus and minus errors were then calculated, and then the delta T's were added in the root sum of squares sense. The result was divided by 2 to give the plus and minus expression. As before, the result is 274.14 plus or minus 1.77 Kelvin. What are the trade-offs between the analytical method and the numerical method? The analytical method requires calculating partial derivatives, which can be a challenge, but a symbolic math program such as Mathematica can make the process much faster and easier. The analytical method can provide insight into the relative contributions or the sensitivity of the uncertainties in each variable to the overall uncertainty. It also results in much simpler and cleaner spreadsheet for calculating the results. The numerical method doesn't require you to remember calculus, which may be an advantage when you're pressed for time. It's harder or less straightforward to see the relative contribution of each variable to the overall uncertainty. The resultant spreadsheet is also more unwieldy and difficult to format to convey the information cleanly. When doing error propagation calculations, you should always be looking for ways to simplify the process. A little uncertainty in the uncertainty is acceptable. So, can we ignore or neglect some of the error terms? And if so, when? Let's look at a simple example. Suppose for our function f, the uncertainty in y is 10% of the uncertainty in x. When the two are added in the sum of squares sense, the result differs from the contribution due to x by 1/2 of 1%, which, given the uncertainty itself, is usually on the order of 1%. The contribution of 0.5% from the uncertainty in y can be safely ignored. The heuristic can then be stated as any individual error contribution, the uncertainty times the partial derivative, can be neglected if its absolute value is 10% or less of the largest contribution. Some rules of thumb are as follows. Except for the thing that you're varying to see the effect, use nominal values or calculated means in your formulas. Choose the error propagation method you understand the best. And neglect any error term that is smaller than 10% of the new maximum error term. The takeaways from this video are: anytime you are doing a calculation or using a formula that involves inputs that have uncertainties or error limits associated with them, you need to use the error propagation techniques and report the result of your calculation with the resultant error limits. The numerical method is straightforward and tedious. The analytical method is elegant and provides insight but requires you to remember calculus. And neglect any error term that is smaller than 10% of the maximum error term. There are not spreadsheet or MATLAB videos for this calculation. We figure that by this point you should be able to do it on your own.